Professor Zaharin Muminov sent me some paper to me, which was very interesting. So then started to study the discrete operator with Zaharin. And then this is somehow extension of this result. So then my talk is only 30 minutes. So then I could not give any details. I skipped the many things. So I only said some essential part. Okay, so before going to the discrete version, I would like to say something about continuous versions. Here, this is h equal to 1 minus 1 over 2m Laplacian plus b. Okay, this is so-called shredding operator everybody knows. And this operator acts on L2 space, L2 RB. Okay, so from the quantum mechanics was founded in 1925. From then, so many results exist about the spectrum of shredding operators. But moreover, this is a shredding operators, but we can extend it to the shredding operator to the relativistic version, which was founded by Einstein. So relativistic shredding operator is given by this, like square root minus Laplacian plus m square plus v. Okay, v is some potential. For example, v equal to minus 1 over mod x. That is Coulomb potentials. But today, I do not say anything about the condition of external potential v. Okay, but this is so-called relativistic shredding operators. So this relativistic shredding operator can be represented in terms of original shredding operator like this. Here, square root of 2m. No. This is error. H should be 1 over 2m minus Laplacian. I'm sorry. 2m plus v. So what is the square root of minus Laplacian to m square? Okay. Here, the property of psi u equal square root of 2mu plus m square. This function has the following properties. First of all, this is positive. Of course, this is positive. Okay. Must say this is strictly positive, and this is greater than or equal to m. Okay. M is a positive numbers, and moreover, psi is infinite times differential function. Okay. Okay. No problem. And furthermore, the third property is very important, and this function. The sign of this function is alternatively changed according to the times of differentiable. Say minus 1 to n times, here psi n equals n times differentiable, and this is always negative. Okay, so these kind of things, the function which satisfy these kind of things, so-called Bernstein function. Right? That is very important. So then we can extend it to the relativistic shredding operator as follows: h psi equals psi h plus v. Okay, psi is some function which is so-called Bernstein function. And here, the second line, this is exact definition of Bernstein functions. Say the example of Bernstein functions is very easy, very easy if you are a mathematician. Okay, so first thing is that Cu to alpha. Alpha is smaller than 1. So you can image that. First derivative is alpha times u to alpha minus 1. Okay, positive. But the second derivative is alpha times alpha minus 1 times u to alpha minus 2. Negative. Okay, so then the sign of function is alternatively changed according to the differential. Okay, so and moreover, a second example, it is also the typical example of Bernstein functions. Okay, so 1, 2, 3, 4, 4. These functions are a typical example of Bernstein functions. Then we define a subset of Bernstein function. This is just we fix boundary conditions. Okay, this is we denoted a B nodes. Okay, B node is a Bernstein function such that if u goes to 0, u goes to 0. Okay. For example, please see example 3. This is not belong to the B node because psi u goes to m. So, okay, but here we put minus m, okay, square root of 2u plus m squared minus m. This is belongs to the B naught function. Okay. So, okay, this is very good. Okay. And the Bernstein function is very much related to the stochastic random processes. I will tell you something. Here, this is so-called Levy measures. This is defining the Levy measures. Definition of Levy measures is very, very easy. First of all, he has no mass in the negative lines, but he has only the mass on the positive lines. Okay, and here y wedge y. This is a minimum of y and 1. Okay, this is finite. This is a definition of Levy measures. Very, very easy. Okay. But next proposition, that is very, very important. Here, psi is a Bernstein function which goes to 0 as u goes to 0. Then there exists some positive number b and Levy measure, class L. Okay. So I missed to write. This lambda is called a Levy measure. Levy measures. Okay. There is a positive number of Levy measure, and psi can be represented like this. Okay. It is very, very nice. And furthermore, if we fix some number b and the Levy measure, then the right-hand side is always a Bernstein function, which belongs to the B node. Okay. So then the Levy measure and the Bernstein function related very much each other. Next, so next thing is the so-called Levy subordinators, a little bit difficult. And here, T of T, this is a family of and some measure of function from YFQ, which is so-called Levy subordinators. Okay, so this is the definition of Levy subordinators. First definition is that TT is a Levy process. Okay, if you don't know the Levy process, do not forget it. So, okay, so, and the second property is very important. That for every omega is fixed, and the maps from T to TT omega, that is non-decreasing for almost surely. So this means that T of T is somehow a random version of time, because which is increasing function for almost surely omega. Okay, so here this proposition says E2 minus UTT. This is a Laplace transform of a Levy process, and here E. This E means that just integral, but in the probability theory, so integral is denoted by E because expectation. Okay, but this is just a integral. Okay, so E2 minus UTT, integration of E2 minus UTT equal to the E2 minus T psi U. Psi is some Bernstein function. Okay. So then, moreover, if the, okay, so, I'm sorry, so there is the units. Okay. Okay, so the, this first statement said that there is, if the psi is a Bernstein function, then e to t psi u always given by this, okay, left-hand side. Conversely, the subordinator tt is given, then the left-hand side equal to the e2 minus t sum Bernstein functions. So the Bernstein function and the Levy measure and so Levy subordinators related to each other said by there is some bijections. Okay, so this is a last line. Okay, this is a Bernstein function, Levy subordinator, and B nu. This is some positive constant, and the nu is Levy measures. Okay, these are the one-to-one correspondence. Then there we can have the following things. Here, B sub t, this is so-called Brownian motion. And here you can see in the Feynman-Katz formula, F times E2 minus T H psi G, okay? So H psi is a generalization of the Schrödinger operator, which is given by the psi minus Laplacian plus B. And the left-hand side is given like this, okay? F times G times E2 minus etc. Okay. So by using this formula, we can have the following things. Here, NV, this is so-called number of negative eigenvalues. Okay, so there are, and a lot of people would like to estimate the number of negative eigenvalues. If there is no negative eigenvalues, it means that there is no, say, ground state, etc. Okay, for example, and Schrödinger operator with Coulomb potentials, he has a infinite number of negative eigenvalues. So this question is nonsense. But some example potential. So okay, we would like to estimate the number of negative eigenvalues. So by using these Feynman-Katz formulas, we can estimate the negative eigenvalues like this. Okay? This is very important. So in the case of Schrödinger operator, this is well known, but this can be extended to the case of generalized Schrödinger operator H psi. Okay. This is the result. For example, this is the typical example of H psi. Okay, square root of minus Laplacian times B. This is a relativistic Schrödinger operator with m equals to 0. So the negative eigenvalue can be estimated like this. Here A depends only dimensions. So one of the biggest problems that we found most small number A, but it is very, very hard problems. Okay. So okay, now in the previous slide I talked about minus Laplacians, but this can be extended to case of many Schrödinger operators. For example, we can add the vector potential A, and we can add the spin here sigma. Sigma is a 2x2 matrices, which is so-called Pauli matrices, but we can add the sigma here. And the second line, this is a relativist version of the first line. All kinds of things can be extended. All kinds of things can be extended to the case of psi, and we can have the Feynman-Katz formula, and we can also have the Levi-Tilling bound. Okay. So anyway, this kind of thing was already established several years ago under these papers. And here, discrete also, we can have the discrete versions. Okay, this was done by Guinness Kellers, but there are many papers. So if you're interested, so please see these kind of papers. Okay. So now we come to the discrete version. Okay, this is the main part of my talk. Here, this is a discrete Schrödinger operator. Maybe everybody knows larger than me. So first line, this is a standard Levy, this discrete Laplacians defined on the L2RD. So by Fourier transform, this Hamiltonian, okay, this Laplacian defined on the torus, L2 torus, and which is given by this F psi. Okay. Then we define the operator L theta. Theta lands on a torus. Okay. Here, okay. TD means 0 times to 0. Okay. D times of 0 interval 0 to D. And now we define L theta like this. This is so-called Laplacian on the torus. Here, this sigma L, that is a spectrum. Okay, so a spectrum of sigma L. Okay, L mean sorry, okay. I did not put some potentials, but we have to put up some potential. There is a blackboard, I cannot say, okay. Blackboard. So, L means L meter plus some potential, okay? Here, this is a delta potential. That is a delta potential who has a mass at x equals 0. Okay. So in this case, here, in the case of dimension 1 and 2, they are here 0 okay. The spectrum of sigma L is this is E is some point spectrum, and the interval 0 to 2, that is a continuous spectrum. Okay, so then nu, this is the parameters, so then nu varying. Okay, so in this case, dimension equal to 1 and 2, there is no eigenvalue at 0 and 2. 0 and 2 is the edge of the continuous spectrum, but in the case of dimension 1 and 2, always there exists a ground state bound eigenvalue E outside of interval 0 to 2. Okay. But in the case of dimension 3 and 4, a little bit changed. And in this case, coupling constant make it smaller and smaller. So some coupling constant nu, then 0 and 2 become yeah. It's not good to use that blackboard. In the case of dimension 3 and 4, here 0, 2. This is eigenvalues. Then the new smaller and smaller, make smaller and smaller. This guy goes this one, and finally this guy attached to the edge of the intervals. But this is not the ground, not the bounded state. So this is called a resonance. But in the case of dimension more than 5, so this is final case, then this eigenvalue attached to the edge of the continuous spectrum, but this is also eigenvalues. Okay, eigenvalue. So then the eigenvalue behavior depends on the dimensions. Okay. Thank you. Moreover, that is a point. Here, nu is here, that is positive. But also in the negative eigenvalues, so then the behavior is similar, but this E appears negative part, but behavior is same as the case of a positive. Okay, that is symmetry. Okay, but now we extended the case of non-local case. This is definition. Okay, here and we introduce some function psi, and moreover, psi is a increasing function. Okay, so then we define a psi node, like a psi L, like this. This is a Fourier transform. Then the psi L is some operator on torus, and moreover, sigma of L equal to the 0 to 2. Okay, then the sigma of psi L is a psi node to the psi 2. This is interval because psi is a increasing function, and we add similar potential nu times delta potential. Okay, this is potential. So in this case, we can see that H nu is represented as like this on the torus. Okay, but this is very, very similar to the case of previous slide. But only the change is that L changed to the psi L. Okay, psi is some function. Okay, C1. Okay, so this is a very easy lemma that we introduce two things, IE and JE. And so then E is an eigenvalue of H nu with some nu if and only if I is finite, J not zero. Okay, this is very, very fundamental lemma. So by using this lemma, we can estimate the spectrum of psi H nu. So here, and moreover, E is eigenvalue, then the nu is given by this. Okay, these kind of things are very, very famous and popular, and there is no hard work. Okay, but this is a corollary, and let E is outside of the interval, but there is an eigenvalue of H nu with some nu. So this means that there is no eigenvalue inside of the intervals. Furthermore, okay. Okay, so then here, curly brackets. Okay, so I have not much time that I slide. Okay, so now we define the two things. Here, psi naught and psi 2, that is the two edge of the intervals, and we define the two things like this. Okay, here this is A, here's a B. Okay. So if the psi satisfies this condition, we call the psi is AB type. Okay, problem. So this is a key lemma of my talk. Psi is let psi be AB type, then the okay, not 1 to 3, 1 to 5. Following 1 to 5 satisfied. If the dimension D is strictly greater than 2 for B, this is equal to psi naught equal. Okay, I'm sorry. And if the suppose that E equal to psi naught, so in this case, IE is finite if and only if this greater than equal to greater than for B. And in the same way, the psi 2, the same result is false. And in the case of psi naught equal to psi naught, so JE is finite if the D is greater than equal to B. The proof is very, very simple. And this is theorem. So okay, a little bit complicated. So the first line, and assume that the psi equal AB type, and this is given, nu C is given by this. Okay, nu C is some typical critical coupling constant, and we assume that the nu is positive. That is very important. So in the case of dimension small, smaller than equal to 2b, so in this case, for all nu, there exists a ground state E. Okay, but the dimension D is greater than 2b, but smaller than equal to 2 for B. In this case, nu is greater than critical point nu C. There is a ground. There exists an eigenvalue E, but nu is smaller than equal to nu C. There is no eigenvalues. Okay, especially nu equal to nu C. There is no eigenvalues. Okay, but in the dimension is greater than equal for greater than strictly greater than 4b. In this case, nu is greater than nu C. There is a ground state, okay, but nu equal to nu C. It is also bound state. That is point. Okay, but nu is smaller than nu C. There is no eigenvalues. So this is table of the statement of theorems. Okay, So in the case of nu is negative, same things happen. Okay. I have 3 slides, and this is example. So this is example very important. And the example of psi is okay, 2 r to 2, or psi u equal u plus la 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 la. This second example is relativistic discrete Schrödinger operators. Okay, and typical example, square root of L plus B. This is a relativistic discrete Schrödinger operators. This is the result. And here, I wrote the figure. So, okay, in the case of dimension 1, not interesting. So, let me see in the case of dimension 2. So, in the positive nu, this guy is eigenvalues. Then nu equal to 0. This guy touched to the edge of the interval, but this is not eigenvalues. But in the case of nu is negative, then the okay, resonance. Okay, no eigenvalue. Okay, but okay. So I'm sorry. So dimension 3, 4. D and 4. It is interesting. So the positive eigenvalues, there exist eigenvalues, but some nu 2. Then this eigenvalue touched to the edge of interval. There's no eigenvalues, but some new node, this is negative. Then here this is eigenvalues. Then the nu is strictly smaller than new node. This is eigenvalues. So you can see that dimension 3 and 4. This is unsymmetry, but usual discrete Schrödinger operators, the behavior of eigenvalue, negative, positive eigenvalue, same. But in the case of relativistic discrete Schrödinger operator, eigenvalue behavior is asymmetries. Okay. So this is the last slide. Here we can consider the 2 things. Left hand side, the square root of m plus m square minus m plus b, and another thing is the square root of l plus b. So left hand side, which is so-called massive relativistic discrete Schrödinger operators. But right hand side, this is so-called massless relativistic discrete Schrödinger operators. But here, you see that in the case of massive, the psi is a 1-1 type. 1-1 type is similar to a usual discrete Schrödinger operator. Then the eigenvalue behavior same, positive part, negative part. But in the case of massless, so as explained in the previous slide, the asymmetry appears. So negative eigenvalue and positive eigenvalue behavior depend. So then the massless case, massive case, their eigenvalue behaviors little bit depend each other. Okay, so the problem is that we would like to consider the similar case, but today I put only one potential, but we can extend this result to the delta potential, but which has a lot of masses. This is a problem. Okay. So thank you very much. Thank you.
Thank you very much, Professor. Any questions? Okay, if there are no questions, then we thank again Professor Fumio Hiroshima, and we continue to next talk, Professor